Hi students, today let me introduce to you the types of semiconductors. So before we move on to semiconductors, let us know what is meant by semiconductors. I have given some words, scrambled words, which you can try it out later so that you'll have knowledge of some terms that are involved in semiconductors. Actually, the semiconductors are the insulators at low temperature and at pure state, whereas they become a good conductor at high temperature and at impure state. And we have two types of semiconductor materials. One is intrinsic, another one is extrinsic semiconductors. The intrinsic semiconductors, where the semiconducting properties of the material occur naturally. That is, they are intrinsic to the material's nature. We don't add anything extra, but these types of semiconductors are pure semiconductors. The most common example of intrinsic semiconductors are silicon and germanium. At low temperature, they behave like insulator, but when the temperature is increased, they behave like conductor. And the extrinsic semiconductor, it is a semiconductor that has been doped. It could be doped either with third group or fifth group. And they are not pure semiconductors. They have different electrical properties than the intrinsic semiconductor. Near all the semiconductors used in modern electronics are extrinsic. This means to say they have been created by altering the electronic properties of the materials. So we have two types of extrinsic semiconductors. One is N type, another one is P type semiconductors based on which is doped with silicon or germanium. Here we have silicon, which belongs to fourth group. The valence electrons are number 4, whereas aluminium has only 3 electrons. Okay, so here you see silicon shares all the 4 valency, 1, 2, 3, 4 valency, whereas aluminium has got only 1, 2, 3. So here there is creation of a hole. Okay, so adding impurities to the extremely pure atom. This is how it has been added. Either third group will be added or fifth group will be added. And intrinsic conductors, we are not adding anything. We have only silicon. All the silicon has 4 valency. Okay, but what happens is when the temperature is increased, this bond will be broken and free electrons will be ejected. This is valence shell, and the electrons present here we call it as covalent bonds. When a suitable form of energy is supplied to semiconductor, then electrons take transition from valence band to conduction band. Hence, a free electron in conduction band and simultaneously free hole in valence band is formed, and this phenomenon is known as electron hole pair generation. In intrinsic semiconductor, the number of conduction electrons will be equal to the number of vacant sites or holes in the valence band. And this is the relationship between the temperature and log of sigma. When temperature increases, the conductivity will decrease. Then extrinsic semiconductors, they are those in which the impurities of large quantities are present. Usually we dope it with either third group or fifth group. Based on the impurities present in the extrinsic semiconductors, they are classified into N-type semiconductors and P-type semiconductors. And moving on to N-type semiconductors, when any pentavalent element such as phosphorus, arsenic, antimony is added to intrinsic semiconductors, 4 electrons are involved in covalent bonding with 4 neighboring pure semiconductor, whereas the fifth electron is weakly bound to the parent atom. And even for a lesser thermal energy, it is released, leaving the parent atom positively ionized. If we consider ND is the donor concentration, the number of donor atoms per unit volume of the material, and ED is the donor energy level. At very low temperature, all donor levels are filled with electrons. With increase of temperature, more and more donor atoms get ionized, and density of electrons in the conduction band increases. So this is silicon doped with phosphorus. Silicon has got only 4 valence electrons, whereas phosphorus has 5 valence electrons. So here, this is the free electron. 4 electrons of silicon and 4 electron of phosphorus will be bound in bonding, okay, whereas the fifth electron will be left free so that it can move around. So this is called impure atom or donor. Whereas p-type semiconductors involves trivalent elements like aluminum, gallium, indium, where they have 3 electrons in their outermost orbitals added to the intrinsic semiconductor. All the 3 electrons of the indium are engaged in covalent bonding with the 3 neighboring silicon atoms, and they need one or more electron to complete its bond. This electron may be supplied by silicon, thereby creating a vacant electron site or hole in the semiconductor atom. So indium accepts one extra electron. The energy level of this impurity atom is called acceptor level, and this atom level lies just above the valence band. And these type of trivalent impurities are called acceptor impurities, and the semiconductors doped the acceptor impurities are called p-type semiconductors. So here you see indium, it has only 3 electrons, so it could form only 3 bonds with 3 silicon. One bond, second bond, third bond, fourth bond it cannot form with silicon, so there is creation of hole. Here we have comparison of n-type, p-type, okay, where here you see in n-type the energy level, we have the energy gap between the valence electron and the conduction band, and here the donor levels, it is very much nearer to donor level, and here it is very much nearer to acceptor levels. So if you are plotting a graph between the temperature and log sigma, for intrinsic range it decreases with temperature, then it attains a saturation range, then once again it decreases for extrinsic range. So even at relatively low temperature, these acceptor atoms gets ionized, taking electrons from the valence band and thus giving rise to holes in valence band for conduction. And due to the ionization of acceptor atoms, only holes and no electrons are created. Thus, holes are more in number than electrons, and hence holes are majority carriers and electrons are minority carriers in p-type semiconductors. Thank you.